Log on, tune in, find out. Another good idea from Cambridge.
Last speaker for today is Erik Koelink from Radboud University in Nijmegen in the Netherlands. And he will be speaking about huge formulas for simple special functions.
Okay, thanks Walter. So I also want to start thanking the organizers for the opportunity to give a lecture here. Well, maybe I was in a strange mood when handing in the titles, but anyway. So the only discrete integrable system will be in this point here. So that's all there is. So there's only special functions in this. And I should also mention, of course, that this work is joint work with Walter Groeneveld, he is in Delft, and Johan Kustermans, who lives in Leuven. This is especially, of course, for Walter, this one. So this has actually been an ongoing project for quite some time, which I, worked on sometimes, and then for a longer time we didn't. And in the end, we finally got to get some results, and it's actually in quantum groups. So actually, the whole thing that was bugging us was to find an appropriate quantum group analog of SU11, which turned out to be really hard. And in the end, we finally managed to find one which is the normalizer of SU11 and SL2C, which actually is more or less 2 copies of SU11. I will not really talk about this, but this is the main motivation for this thing. So let me give you an outline of the talk. Well, I already started with the first part, the motivation. The second part is try to get this one. Oh yeah, what are the simple special functions I want to discuss? You see, nowadays, as you can see also in the previous talk by Mitsan, you have, of course, you can write down huge special functions. I mean, you can go up to the level of 453s, which is considered elementary nowadays. 8v7s is still more or less elementary, and then you go up to 10v9s, and you go into bi-orthogonality, or even 12e11, whatever. So elliptic functions, so you go up higher and higher. But this will be very simple special functions, so I will be able to have them on my slide. But the formulas for these ones, which I want to derive, I'll show you an example of, they are going to be big, huge. And I want to give you an appetizer, so you start with this one. So this is actually a positivity result. So the nice thing is that I don't have to write the right-hand side, except the fact that it's bigger than 0. And of course you can write down this whenever you like, because I didn't really say what these special functions are, so I should explain. So these are the ones in red here are the Q-Laguerre polynomials. If you are familiar with them, then it's easy. And this is the explicit expression for these Q-Laguerre polynomials. So they are basic hypergeometric series of level 1 phi 1, which I consider to be simple. And this is for the special case where the parameter alpha equals 0. And if you're not familiar with this notation, this is the explicit formula for this polynomial. And what I also, so here I have the polynomials, and here they are polynomials, the same polynomials, but now you multiply the argument with an additional q to the power a, and a is in an integer. And this red part here, q to the power k in the numerator and minus q k, this infinite product here, defined in this way, in the denominator. If you only take out this part, this red part and this one, this is one of the orthogonality measures for the Q-Laguerre polynomials. The nice thing, or maybe the annoying thing, depends on how you look at it, these Q-Laguerre polynomials, they are orthogonal, but they are orthogonal for several orthogonality measures, so they correspond to an indeterminate moment problem. Okay, so this is one of the examples. I will hopefully sketch a proof of this one. Okay, so let me start with the motivation. So I need to say something about what a quantum group is, and I decided to do this only by looking at a group. Okay, so I put the quantum in between parentheses, and this is the definition I want to follow is by Johan Kustmans and Stefan Vaas, also from Leuven. So I did my best to put Leuven on the map today. It's a lovely place. You can go there in a couple of weeks' time if you like. So I'll have a Lie group, and I consider all the space of bounded functions on G, and I consider this to be acting on K, and K is just L2 of G corresponding to the left Haar measure. Okay, so this is, and the next thing I will focus on, this one is, so I'll not give the precise definition, but I will focus on this W here. This is an operator of K tensor K to K tensor K. And in the classical case, this is a very explicit formula. So W of F is just that you mix the two arguments of the functions. And then it's easily checked that this is unitary. So if I first apply W and then the W star, the adjoint, then you get the identity, and also the other way around. So this is easily seen to be a unitary operator. And moreover, it satisfies the pentagonal equation. I will get back to this one in the next slide. I will hopefully explain what it does, what it gives. But the important remark I want to make at the moment is that if you have this W, then you can define this map, capital delta, and delta of x is just one tensor x. X is an operator on your Hilbert space, K. And this is just the multiplication by this function x. I view x as a function, so multiplication by x, and then you conjugate with W. And if you work out what this definition and that definition gives you, then it just means that if I think of this delta x of an operator on a function of two variables, then it's just multiplication by x evaluated at g times h. So this co-multiplication encodes the multiplication of the group, right? This is the important remark. And the other remark I want to make is that maybe later on, or yeah, so at this point you see that if I would look for representations of M, then I can, well, I view delta going from M to M tensor M. If I take two representations of M, and I first apply delta and then one of the representations onto M and the other representations on the second factor of M, then I'm getting a tensor product of a representation. Well, in this case it's not really very exciting because you get, this is all commutative as an algebra, so there's no point. But what it says here is that this W will give you some kind of decomposition of tensor product formula. So these W's, these multiplicative unitaries as they are called, they actually can be thought of as a kind of intertwining tensor product with the direct or integrals, direct sum or integrals of representations. So they have a kind of role as Glasgow coefficients, if you like. Okay, so, well, at this point it's not really that relevant. So let's focus on the pentagonal equation. Okay, so actually it's easier to do this for the adjoint, because then I don't have to take inverses, and then it's a bit easier to see what's going on. So the pentagonal equation says that if I start with a function of three variables here, I apply the adjoint of W2, 3. Well, I should explain maybe what the leg numbering is, right? I forgot. So what does it mean? Okay, so W1, 2. So W12 is W acting in the first two variables, and the identity at the last one, and W13 is that you have it act on the first and the third component. W23, it acts on the last two components. So this is a standard lag numbering notation. So let's go to this one. So this is what we need to view. This is that we start here with a certain function, three variables in G. we want to apply W to 3, the adjoint of it, again this one, and then end up here. And the other way, we should also be able to go like this, and they should have the same outcome, right? This is what the pentagonal equation says, and so what I did is to have some abuse of notation. I put it in what it means. So if I start here with the function of, say, st and r, so let me go back this one. Then you see, so what W star, the adjoint of W does is it leaves the first argument unchanged and it multiplies the first and the second to the in the second argument. So what it does here is that W12 star here, so it replaces t by st, and so this is the first map. And then the second map, you do the same thing, but now for the s and the r, so you get this one. And then the last one, you do this for 2r, so you look at the t and the r, so you replace t like this, and you replace the second r by tr, so you get this one. If you go around like this. And if you go the other way around, then you first apply this on the second and third argument, you get t and tr, and then you have to do it once more, s and t, so you get this one. So the only thing that matters is that the first two arguments are okay, and the third argument is that this is st times r, and this is s times tr. So what it means is that just you assume the group to be associative, and then these two are equal. So what this says, this pentagonal equation, it says that there's associativity in the group. Okay, so this is the pentagonal equation. And an operator which is unitary, like this, and satisfies this pentagonal equation, this is called a multiplicative unitary. Okay, and actually I will focus on this one, and this is an older idea by and Skandalis from 93, if I remember correctly. So this is an idea to encode as much as you can of the group in terms of a single operator. Okay. Okay, so the other thing we need, well, if you have a group, so this one acting on this Hilbert space, K, L2 of G, then I can look at its matrix coefficients, if you like, right? So F1 and F2 are elements of your Hilbert space, and you look at the operator X acting on F1, taking inner products with F2. So these are linear functionals, and these are special linear functionals you need to have, normal linear functionals. And in the case of the group, this is just xg integrating with respect to F1g and F2g bar. Now I'm going back to and taking a definition of Customans and Faas, and this says that if you have this M, then you can define an M hat, which is also turns out to be a von Neumann algebra with a suitable co-multiplication. And what you do is you take this W, so this multiplicative unitary, which acts on K tensor K, and you take such a typical functional like this one, you take in the first leg. So you end up with an operator going from K to K. And the set of all these operators, they form together, they form a von Neumann algebra if you take an appropriate closure. We'll not worry about this. So you get a set of operators, again, in B of K, this Hilbert space K. So let's try to find out what this omega tensor identity acting on W actually does in this case. Well, if you look at what happens, so I take this omega of this form, this normal functional in this one. So I have to let it act on a third function, say F3, and I evaluated this at H. So what does this omega F1, F2 do? It means I'll take W, let it act on the F1 tensor F3, which I view as a function of two variables. I take the inner product with respect to the first variable in this L2 space with respect to F2, so the first variable here, and I still have the second variable here. So if I write out what this inner product means, just this, and if then I plug in what the definition of W is, then it's just leaving F1 as a function of G, and F3 I take it as a function of G inverse H. And what this says is that it's just, so if lambda denotes the left regular representation, this is just the integrated version of the left regular representation of the product of F1 and F2 bar acting on F3 and H. So this these type of operators, they occur in the left regular representation of the group. And so this is to be considered to be this dual von Neumann algebra. Okay, so this is the sketch of the, say, the classical situation. And now we are going to do this in a somewhat non-commutative setting. So we'll go to von Neumann algebra, which is no longer commutative. And I will, this will be my key Hilbert space. So that now K used to be L2 of G, so it's now becoming L2 of the circle times L2 of IQ, tensor L2 of IQ, and we'll also recall that IQ, so that this will be minus Q to the power N with Q to the power Z, so you think of these as points on the real line, etc. And well, this used to be my convention at the beginning, but N doesn't contain 0, so be careful. And they, of course, accumulate at 0. So this is the Hilbert space we will work in. And of course, now we can take this orthonormal basis from now on, FMPT. So M is in Z for this space, and P and T are elements of IQ. So this is the standard orthonormal basis for this Hilbert space. And this is the Hilbert space. This will play the role of L2 of actually the quantum analog of that group there. So this is the space we will work in. Now there is a general construction how to get to this space. I will not go into that. Now the point is that we have been able to find a multiplicative unitary which does the trick. And so and I will come to this this part. And I want to explain why it satisfies the pentagonal equation, and in particular, once you have this pentagonal equation, what does it imply for the special functions that are around? So this product of two series will be two basic hypergeometric series. Okay, so this is the switch. So we now more or less understand what this W and this Hilbert space are for the classical group situation, and now we want to apply this in the quantum group analog of this group. Okay, well, this already I told you. So now what I will do is I will have this, well, what I had this omega Fg, so this functional again, this normal functional again. Now I will apply it to W star, and this will again be an operator of K tensor from K to K. And for this F, I'll take some specific elements. So there will be a 0. So this is the FMPT, this definition of these bases here, and I'll take this G over here. Whereas this this functional is given like this as before. Okay, there is a slight change in definition, because on the previous slide I said that the dual von Neumann algebra was going to be generated by this type of operators, but then with W instead of the adjoint of W. Well, there you have to work a little bit in order to get this done, but it's not that that hard. And then what you can show is that actually these operators, well, you have to do some work, but these operators actually span this this von Neumann algebra that is being defined in this way. So we get a linear span for this kind of operator. So you could think of these as a kind of generalization of convolution operators. Okay. Now these operators, okay, once you know that they span this von Neumann algebra, you can wonder what is the structure of this von Neumann algebra. Can you say something about their structure coefficients? Well, I have to explain, of course, what these A's here are. I will do so in a minute, and I want to explain at least how you can get into this formula. But this formula that you have here, so that this product of these two typical operators in the dual von Neumann algebra, that they expand in a very nice fashion. So the structure coefficients are very nice, that you can get this from the multiplicative property of the pentagonal equation of the multiplicative unitary. But you see that there is a serious condition here and here. There should be two conditions relating P1 and P2. So recall that P1 and P2, they are in this space IQ. So I can look at that quotient, that should be q to the power m, and this is the m. So the P1, P2 here and the m here are related, and similarly for the R1, R2 and the n over here. So, and most of the time the product is 0, but we'll be mainly interested in the cases that this product is not 0. And the other thing which I will not use is that you can also calculate this dual co-multiplication on these generators, and it gives also quite a easy expression, a double sum, but you see that this is more or less straightforward. I will not discuss this. This will end up in even bigger formulas at the end. So okay, so I will focus now on these operators Q. So recall that P1 and P2 are in this IQ, so they are of this form, and n is an integer. So they are labeled by 3 parameters, and these type of operators I want to discuss now with you. Okay, so maybe I will first explain now what these coefficients are. So these coefficients, you see that the multiplication, these structure coefficients, they factorize nicely, and in the dependence that R1 and P1, so the P1 R1 are together and R2 P2. So this is a very nice factorization, which should remind you somehow of kind of addition type formula for special functions. Okay, so now I'll go back. What are the simple special functions that we want to discuss? Well, so I recall this definition of these Q shifted factorials here. So Q is always between 0 and 1. This is a Q shifted factorial, contains K factors, and then of course you can let K tend to infinity because Q is less than 1. Okay, so I will use this notation. This is actually a 1-by-1, but I multiply this with this infinite product, this Q shifted factorial concerning B, because it has the advantage then that this psi function is analytic in A, B, and Z. So this is the advantage of writing it like this, so we don't have to worry about the case that in case B is Q to a negative power. Okay, so and the other special function that will come later, but because I'm introducing the basic hypergeometric series here, is that the 2-by-1 is also going to play a role. So if you've never seen it before, this is its definition. This function here is, so it's analytic in Z, but this one has a finite radius of convergence, but it can be analytically continuation is possible, and this will always be done. So now I need some additional notation, just well, in order to keep the formulas on one slide, I need to introduce a little bit notation. So chi is just the Q logarithm of the absolute value. Kappa is just a squared, but you take into account its sign. Nu is Q to the power half chi of t minus 1, chi of t minus 2. So this decays very fast. If t goes to if t goes to infinity in qz, or to minus infinity in minus qz. And this s, this is just a sign. So this sign is, well, you see that this is almost everywhere minus 1, except that it's plus 1 in the second quadrant, right? So this is just one particular sign. And this is just a normalization constant, well, okay, in order to make the formulas complete. So for especially this chi and this kappa, they play a role. Now I can define what these special functions are. So they're all 1-by-1s, and it's this one. So I'll consider A for a P in IQ. So this IQ again, minus Q to the power n and Q to the power z. And this is a function of two variables, x and y. X and y are also in this space IQ here. and the support of AP is a line. The support is that the sign of x times y has to be the sign of p. And then it's this function. So this normalization constant, this sign, this is also a sign. This is an elementary factor. This is the 1 phi 1, and the square root of this thing here. So this kappa p. So this is p squared times the sine of p. It's chosen in such a way that it's nicely related to certain measures, orthogonality measures. But you can immediately observe that this this square root is always taking a square root of a positive a number. So this never becomes negative or 0. So this is this function AP. And what you also should observe is that psi terminates. Maybe I should have said that before. For y in minus q to the power n. Right. So because if y is if y is in minus q to the power n, you get kappa of y is a sign, so the minus sign drops out, and you get q to the power 2 minus chi of y, and then this is a negative integer, so then it terminates. So this terminates for all y in minus q to the power n. So this is a straightforward definition. Now I should explain where it comes from, but first maybe to show that there's a p, there's an x, and there's a y, and there are certain symmetry relations involved. So you can interchange any of these pretty easily, except that you have to pay the price of a sign plus maybe an elementary factor. So you can interchange p and y, you can interchange x and y. This is only up to a sign. And of course, if you have these two, then of course you get the last one as well. And these are just, well, the transformations that are the basis for these symmetry properties are just limit cases of Highness transformation formulas. So this is fairly straightforward. Okay, of course you still don't know where they come from, but okay, so this is the definition of this one. So, and now now comes a bit of an awkward moment, and so every talk should have an awkward moment. This is mine, so I have this awkward moment, the scary part. But this is this. So I did try to make it into a nice drawing, but I didn't manage to get it from in later beamer. So I had to scan this silly drawing. So I want now to explain what does it mean. So this is actually the AP of xy. So x is on the horizontal axis, y is on the vertical axis. It's even missing, but it should be there. Because of course this should be somehow be related to known special functions, because they're only living on the level of this 1 phi 1. So they should be very well known. And the thing is that if you take if you're sitting on, say, on this line, so this is a line going through this IQ times IQ, so this should be discontinuous, so these are these points. Then you can identify these 1 phi 1s up to this factor in front, so I'll forget about this factor in front. These are Alsalam-Karlitz polynomials. So they're Alsalam-Karlitz polynomials on this line, so for x negative, y positive, this is Alsalam-Karlitz, and because you have the symmetry in x and y, you get also Alsalam-Karlitz here. In this third quadrant, they are related to this Q-Laguerre polynomials I was starting with, so they will pop up later again. These Q-Laguerre polynomials, as I said, is corresponding to an indeterminate moment problem, and there is a certain complementary set of functions, and they live in this first quadrant, and they are Q analogs of the Bessel functions. They are big Q Bessel functions, and you can get them if you want from a limit transition of the big Q Jacobi polynomials. Anyway, they are explicit, and there is an explicit orthogonality for these functions and and so on. Okay, so I did my best at this drawing, but it's not optimal.
What we get here?
Sorry?
What we get in this region?
Which region? These are arbitrary lines, right? So this is you have to, so this is representing an arbitrary line with negative coefficients and an arbitrary line with a positive coefficient. Okay. So in principle, first quadrant, big Q Bessel functions. Second, Alsalam-Karlitz. Third, Q-Laguerre polynomials, and the fourth again, Aslam-Karlitz polynomials. Okay, then we have orthogonality relations, because we can just use the Aslam-Karlitz polynomials. This is the Aslam-Karlitz orthogonality. Now you see that the square roots of all these infinite products involving these kappas of p, x, and y's, this is just the square root of the weight function involved, so that there's not a weight function over here. And what you get, so this is typically such a line I had drawn in my previous picture. And then you also get the dual orthogonality relations. These come in for free, and so the Aslam-Karlitz orthogonality sits in here, and here sits the Q-Laguerre orthogonality. So it sits here in the dual orthogonality relation. So in some sense, this picture I had here is deceiving, because the orthogonality here is the orthogonality of the Aslam-Karlitz polynomials, whereas for these ones here, this is the dual orthogonality, right? So it's not the same. Okay. Now I finally can define what my multiplicative unitary is here. So it's you see it's so M1 P1 and T1 and M2 P2 T2. So M1 is in Z, and P and T are in IQ. And now this is this double sum. Okay, so it means that this W is indeed, most of the time, has 0 matrix coefficients, and if it's non-zero, then it's a product of these two 1, 5 ones. And here you see how this can explicitly be worked out. So how do you get to this formula? This is, of course, a point. Well, the point is how to get to this formula is precisely what I told you about these Klebs-Gordon coefficients. So what you do is, so going back, if you know, there is a certain Hopf algebra for quantum SU11. You can try to decompose, for at least formally, irreducible representations, and if you do so, then you run into huge problems related to the fact that you run into operators which are no longer nicely self-adjoint with a nice spectral decomposition. But if you adjust this a little bit, then you get into difference operators which have these A's as solutions, and these A's occur then as coefficients, so as a kind of Klebs-Gordon coefficients, and then you can prove that really that W is indeed a multiplicative unitary. And actually the unitariness, that just follows from the orthogonality relations, but the fact that the multiplicativity, so the pentagonal equation, for this you really have to work hard, and for this pentagonal equation it's really essential that you have put in this awkward sign, this S of xy, otherwise it doesn't work. Okay, so now I want to find out, well, now that we have this W explicitly, we can write down these functions Q, these operators Q explicitly. So here they are, the matrix elements. So you get a lot of deltas. It's a lot of times it's just 0, and if it's not 0, it's a simple product of these two 1, 5 ones. Okay. Okay. Now I want to sketch at least a proof of these structure formulas. How does the pentagonal equation come in? So let me give a proof. So, well, at least a sketch of this proof. So, well, this is straightforward. Now you see here the adjoint of W23, the adjoint of W13. You rewrite the pentagonal equation like this, you plug it in, and you get this identity, and now you are something which is pretty close to such an operator Q if you have picked F and G of a suitable nature. But since I know this W explicitly, I can work this out, and you get a huge sum, 4-fold sum, this one. They are coming from the fact that you know the explicit matrix coefficients of W, and you get this one, you get this one, but here you get an inner product of these two orthonormal bases, so this gives you at least 2 Kronecker deltas, and I have to identify this last piece here, and for this you use that if you take an arbitrary M1 P1 T1 and an F M2 P2 T2, that this is another Kronecker delta times the Q's I want to have. Okay, and now you see that you get 3 Kronecker deltas, and you will find out that it is 0 unless this condition holds, and if this condition holds, you get precisely what you want, except that you have to evaluate this huge sum. Okay, and this sum you can now apply. You can note that this sum is again 0 if you have a certain condition, this immediately follows from the way these A's have been constructed. And if this condition holds, then you can use one of the symmetry relations to find that it's this sum, and this is one of the orthogonality relations, and you get 1. Okay, so it ends up pretty smoothly, and so what we finally found is this structure coefficient formula. And you see that this is very nice, so the obvious thing is what you want to do is to represent this. And that's where big formulas come from. So let me represent this one. So I'm taking matrix coefficients of the identity, and this will give you a straightforward identity. So I'll take so special choice for f, so minus L, epsilon, eta, p, q to the power L, z, and z. So and L and M are in z, p are in q to the power z, and z is in iq, but I assume that it is sine epsilon. Will not explain where this comes from, but this is the way we ended up with them. And we know that we have to take in the right-hand side an orthonormal basis vector of this type, otherwise you'll get 0. So you have to take it of this form, and so the freedom is this W, and all the other ones are more or less fixed. And then what you have to do is that, of course, you throw this one to the other side, expand it, calculate its matrix coefficients, you get a single sum, and I didn't specify where this u is coming from, but what you get in the end is you get a single sum of a product of 4 of these functions, a, p, these simple 1, phi 1s. Okay, now once you have this, you have to do the same matrix element for the right-hand side. So you start with the right-hand side. Of course, you have to evaluate them with respect to the same basis vectors, and you do this again. And again, you get a single sum of 4 functions of this type. So these two are equal. So you get this formula. So I wanted to have at least one formula which is really big, huge. So it's in here, and in this formula I really specified everything where you should take the sum over. So P1, P2, R1, R2, they are in this IQ. L, N, M, Z are in Z, L and M are in Z, and epsilon, eta are signs. Okay, so you see that this is relatively simple, but here it's getting more difficult, here it's getting also more difficult, and here you get nasty exponents. And then this sum here, you should observe that this sum, if you look at this sum, this is a sum over IQ, but you see that there is a constraint on the sign. So the sign gives you that you sum either over q to the power z or over q to the power n. So it's either a sum over c or over n. And similarly here, this is either a sum over z or over n. So it's either one of them. And of course what you can do is pick your choice, and you get a formula for Q-Laguerre polynomials, or for Q-Bessel functions, or for Aslam-Karlitz polynomials, or whatever. So this is if you want a kind of master formula encoding all these stuff. Okay, so this is actually the only huge formula I want to show. I kicked out the other one because it didn't fit on the slide. But now I want to show you how the first formula I started with, how you can derive this from this setup. Well, the thing you need to know is that if I take the adjoint of such a simple operator, then I get a simple operator of the same type again, only with n switched to minus n and up to some elementary signs and powers. So if I do this, then of course I get this identity by specializing this product formula, this structure coefficient formula. I get it of this type. And of course then the nice thing is that the left-hand side is a positive operator, and this positive operator will give me the greater than 0 part. So what I then get is, by doing the same calculation, if you like, you get that this sum is always positive. So this gives you a positive result, and at least I want to make one specialization. So I take R1 to be negative, Z1 to be negative, R2 to be negative, and also this thing here to be negative. Then you see that you're always in this A function, which is in the third quadrant, where they are Q-Laguerre polynomials. And if you then work out what it is and you have some signs, you finally get back the formula I started with. So this is one consequence of this formula, of this positivity result, which you get for free. Okay. So now at least I've proved the first formula. Okay, so well, I told you that This is all motivated by trying to understand what the operator algebraic interpretation is for this quantum group analog of the normalizer of SL2C, the normalizer of SU11 in SL2C. And as you know, SU11, there's a very well understood quantized universal enveloping algebra around, UQ of SU11, this quantized universal enveloping algebra. And actually you can have this in this interpretation, and I just wrote down an action of an operator E0 and an operator K0, and this acts on this basis vectors, these FMPT, so they act on this Hilbert space K, and you see that it can blow up because it depends on P, this can be large, so everything can blow up. So these are unbounded operators, so I consider them to be operators defined on finite linear combinations of the basis vectors of this orthonormal basis. But you can straightforwardly check that these relations hold where the dagger stands for the formal adjoint, but then restricted again to finite linear combinations of the basis vectors. So this is, what I get is a realization of the quantized universal enveloping algebra in this way. And it's a faithful representation of this one. So now the question, of course, is how is this related to this dual von Neumann algebra? And there's a bit of a tricky part. Oh yeah, of course I need to introduce the Casimir operator. The Casimir one is this one. And so I think of this omega naught as an operator defined on finite linear combinations of these FMPT. And normally you would say, okay, this has to be a self-adjoint operator. Well, it's symmetric, but it's not essentially self-adjoint. This is a bit of a nuisance. So there's a whole family of self-adjoint extensions. So the problem is, how can I choose the right extension of this one? And that's the following result. So you have to take the self-adjoint extension that is affiliated to this von Neumann algebra. So then you have to know what affiliated means. Affiliated means that it commutes with all unitary operators in the dual von Neumann algebra. So actually, so that you can look at it as like this. So omega is a self-adjoint extension of omega naught in such a way that it would have been in the von Neumann algebra M hat, except for the fact that it's an unbounded operator, right? So, and actually this condition here, this affiliate, this is precisely determining the self-adjoint extension that you need. And well, and then what you have is that this operator omega does not commute with the Q's I introduced previously, but it almost commutes. It depends on the sign of the product of P1 and P2. If this sign happens to be positive, it commutes. If the sign is not positive, it's anti-commuting. So what you see is that these Q's, what you see is that omega is not sufficient to generate a dual von Neumann algebra. In this case, you need more Q's as well. Okay, so this is a side problem for this talk. But anyway, what this suggests is that these Q's must be very nice in eigenvectors of the Casimir operator. So these Q's must act nicely in terms of the eigenvectors of this Casimir operator. So what we need to do is to find the spectral decomposition of the Casimir operator, and we can do this explicitly. So this is a kind of polar decomposition, except that we have to have a projection here as well. So any Q is some partial isometry times some function in the Casimir operator times some projection. This is a projection related to the spectral decomposition of this operator K, if you extend this. And this H is a very elementary function because it's a 2 phi 1. So this is hard work to get this done. But essentially well, there's a nasty constant in front, but it's essentially a 2 phi 1. So any Q is essentially a 2 phi 1 in this Casimir operator. This is very nice because if I take this link now again and I go again to my structure coefficient formula, now I know that this acts nicely in the spectral decomposition of the Casimir operator, this one as well. So I get another formula from this structure coefficient formula, which is, well, this was too big to fit on the slide, so I put elementary factors for a whole bunch of factors, but essentially this 2 phi 1, 2 phi 1, they come from this product in the basis for eigenvectors for the Casimir, and these psi's, they are the A functions A, and this is the operator Q on the right hand side in the sum, where you get this enormous formula in this way. So you get that for free out of the context of the structure coefficients. Okay, well, I think being the last talk of today, I should certainly not go over time, so I'll come to some final remarks. So you can also get other formulas for this Q, and you get similar. You get some like a single sum of 2 phi 1s times the size is a product of 2 phi 1s. All comes out for free. You can do the same trick if you like for the co-multiplication. You get even bigger formulas. They become really huge. So you get all kinds of special functions identities, and I should also say that this was not a goal we set out to at the beginning, but what we wanted to do is we wanted to describe this dual von Neumann algebra, which you get in a general abstract way. You want to actually to write this down explicitly as what kind of generators do you get. So what we can prove is that the operators E and K, which are the closures of these unbounded operators, they are not sufficient to generate a dual von Neumann algebra, but you have to throw in 2 additional factors which you actually deduce from this polar decomposition of these Q operators. So this was actually our main goal at first. Now going back to the group theoretic interpretation, so we started with this dual von Neumann algebra for the group setting, and then you see that this M hat is essentially the left regular representation. So here you should have the analog of the left regular co-representation. And what you can do then is decompose this explicitly in terms of discrete series representations and also principal unitary series representations. That's precisely the 2 types that occur. Of course, I didn't explain what they are, but you could, well, the discrete series are just the ones that really sit into the left regular co-representations, and we can really construct them. And by using analytic continuation, you can also define what the complementary series representations should be. So for this quantum group analog, you can easily, well, easily is not a word, but you can, in the end, you can write down what the co-representations are on an analytic level. So this is all really on an analytic level in terms of von Neumann algebras. And then you get bi-orthogonality relations as well. Most of the time they're actually orthogonality relations, but and they are related to the fact that you also have an indeterminate moment problem for Q-Meister polynomials, but this is an observation at the end, afterwards. Actually what the orthogonality relations are nothing but the fact that you have unitarity of the co-representations. And writing out the unitarity of these co-representations for the principal unitary series gives you these orthogonality relations. So we posted this about 2 months ago on the archive. And this is a small sample of what's in this paper. So many more huge formulas, if you like them, you can find them over here. Okay, thanks.
So from the perspective of orthogonality of these orthogonal polynomials with indeterminate moment problems, it seems a little unnatural that you have these 2 geometric regressions.
Yes.
And you've related their base points in a very special way. And for the actual indeterminate moment problems, I don't think you need that relation at all. No, so it seems like there ought to be possible to put another parameter in.
Yes, that's precisely what happens. So if you look at this last point, for instance, you get out orthogonality relations or bi-orthogonality relations for this indeterminate moment problem. And once you have these on paper, it's immediately clear that you can put in 2 additional parameters, right, which are continuous. But these are usually, they are not contained in the quantum group theoretic interpretation. And this is something that occurs, very often, that you get some interpretation of special functions for discrete sets of parameters involved. And once you have the result, you can immediately see that you can extend this in these set of parameters. But it doesn't come out in this way. You have to observe this once you have written it down, what it actually is.
So sort of what in the quantum thing is forcing 1 and -1 as opposed to -1 and alpha, or?
Oh, yeah, that's a good question. Yeah, but this is not really okay. So this is where these APs come from, and of course you could have put in some additional alpha in here or over there. It would have meant that you would have to change the APs accordingly. So you essentially end up with the same problem. There was a choice at a certain point. There is a choice in finding the suitable self-adjoint extension of an operator leading to these Clebsch-Gordon coefficients. But this choice somehow is, well, it seems to be that there is a choice, but this choice is forced upon you once you really want to prove that the pentagonal equation holds. So this is essentially that you prove that the co-associativity of the co-multiplication is true. And then you get forced to these sign choices. But I agree, if you would have stretched this a little bit, you essentially get the same result. Yeah.
Anyone else? No? Just to thank all the speakers of this afternoon.